This lesson's about Newton's law of gravitation and gravitational fields. So first, Isaac Newton didn't discover gravity. We have this idea of him sitting under an apple tree getting hit by an apple and discovering that gravity exists. But of course, people knew that gravity existed before that. What Newton did was that he recognized that it was universal. So this is sometimes called Newton's universal law of gravitation, that it applied to things on Earth, and it was also what was keeping the planets in orbit around the sun. And he also found a way of quantifying it. He recognized that the gravitational force is proportional to the product of the masses of the two objects that are attracting each other divided by the square of the distance between their centers, r being the distance between their centers. So it's what's known as an inverse square law. As the distance between their centers increases, the force decreases by a factor of 1 over that distance squared. Now, this is a statement of proportionality. By introducing a gravitational constant g, which has this value, we get an equation. So the gravitational force is equal to 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared times the product of the two masses, and again divided by the square of the distance between their centers. And really, as it's stated here, this equation works for particles, but we can also apply it to spherical objects, as I said, if we treat r as being the distance between their centers. And for non-spherical objects, it can work as an approximation. So let's take a look at an example. Find the gravitational force acting between a 50 kilogram human and a 1 kilogram textbook that's 1 meter away. All we do is we plug in to this equation. So we're going to plug in our gravitational constant, which is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared multiplied by 50 kilograms by 1 kilogram and divided by 1 meter squared. And when we plug that into our calculator, we get approximately 3.3 times 10 to the negative 9. The units are newtons. Kilograms squared cancels with kilograms squared, and meter squared cancels with meter squared. So we get newtons, or approximately 3 nanonewtons. So a very, very small gravitational force. The only reason why the gravitational force that we experience every day from the Earth is relatively large or noticeable is because the mass of the Earth is really, really big. Now let's talk about gravitational fields and gravitational field strength. When we start to think about forces like gravity or the electrical force that acts between two charged objects, we're now talking about forces that act at a distance, and we need a model for thinking about those. Fields give us that model because a field is a region in space where a force is felt. Imagine that you had a vacuum with nothing there, and then all of a sudden you put a planet in it. Now around that planet there will be a region where gravitational force would be felt. For example, if you place a test mass around that planet, that test mass would now feel a gravitational attraction towards the center of the planet. And we could draw that gravitational attraction as a vector. If you were to move it closer, it would feel a greater force. And we could quantify that force. Let's say we measured it, and here the force felt was 3 newtons, and here the force felt was 12 newtons. We could do that all around the planet, and we would see first that that force field, that vector field, is symmetrical, and we would be able to quantify it at all these different regions. All these vectors are pointing towards the center of the planet, and they're indicating the force that would be felt by this test mass. Well, let's say the test mass was 1 kilogram. Now each of these become newtons per kilogram. And if we were to double the mass of this test mass, it would double the total newtons, but not the newtons per kilogram. So this is a way of standardizing for the amount of force felt. It's the newtons per kilogram. And this is how we represent field strength. Field strength is the force felt per unit mass. So the force felt per unit mass. Force is in newtons and mass is in kilograms, so our field strength is going to be in newtons per kilogram. Now, we know that the gravitational force is equal to g, our gravitational constant, times the product of the two masses. I'm going to call this big M and this little m, divided by the distance between them squared. And because this is standardized per unit mass, I have to divide out the mass of the test mass. Those cancel, and I get big G times the mass of the object creating the field divided by the square of the distance between the centers of that mass and the test mass. Again, the gravitational field strength is equal to big G times big M divided by r squared. By the way, recognize that newtons per kilogram also simplifies to, because this is equal to kilograms meters per second squared, simplifies to meters per second squared. So the units simplify to meters per second squared, and also notice that if the only force acting on an object is the gravitational force, then F net is equal to the gravitational force, then the field strength, which would be F net here divided by m, is equal to ma divided by m, and we get that the field strength is numerically equivalent to the free fall acceleration. The field strength is equal to the free fall acceleration. It's important to recognize that the gravitational field is a vector field, and so adds like vectors do. So if you have multiple objects like we see here influencing the same space, then the net gravitational field is the sum of the gravitational fields of each of them. Let's say we had two identical planets here, we'll call these A and B. Then in the space right in the spot right in the middle there, the force felt, if there were an object here, would be equal and opposite, and the gravitational field strength in the middle would be 0. So just remember that the gravitational field is a vector field and needs to be added like one. Let's do one final example. Find the magnitude of the gravitational field strength at the Earth's surface given its mass and its radius. So the gravitational field strength is equal to g times the mass of the Earth divided by the distance between the centers of the two objects, the center of the Earth and the center of the test mass on its surface. So this is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared, multiplied by 5.98 times 10 to the 24 kilograms, divided by 6.38 times 10 to the 6 meters squared. And when we put that into our calculator, we shouldn't be surprised that we get 9.80 newtons per kilogram. And again, those units are equivalent to meters per second squared. So that's an introduction to Newton's law of gravitation, gravitational fields, and gravitational field strength.